Hello. In this video we are going to look at temperature. This perhaps seems a little rather pointless. After all, you probably think you know what temperature is. But let's think about it a little, eh? So what is temperature? Well, you might answer it's how hot something is. To which I would reply yes, but what is it that characterizes things that are hot? Their temperature. Now hopefully you can see that the logic here is somewhat circular. In fact, the more we think about it, the more slippery this concept of temperature feels. For example, I have repeatedly told you that the state of a system, the way that it behaves in the absence of any external agent acting upon it, is characterized by the values of its extensive thermodynamic variables. Temperature is intensive, so even our answer that temperature is how hot something is now seems wrong. This answer implies that temperature is a property of a state of the system, but it can't be because the state of the system is characterized based on the values of the extensive variables, and well, temperature is intensive. This temperature thing is pretty confusing now. We are now comfortable with temperature as a concept thanks to the work of numerous 19th century physicists. We learn about it rather early on in our education, which can, I think, make us be rather blasé when it comes to thinking about what temperature actually is. So with all that in mind, let's give these 19th century physicists their due and actually look into what this temperature thing actually represents. Remember from my previous videos that I explained that these 19th century scientists were interested in heat and work because they were interested in how a steam engine worked. I said that in these engines, a gas is heated or cooled down, and as a consequence, it expands or contracts. I then explained how this expansion of contraction of gases could be used to drive machines and to do Newtonian work on objects in the environment. We had concluded that, because Newton's third law tells us that every action has an equal and opposite reaction, work had to be transferred from the system, the gas in the piston, to the environment. I had further argued that it should be possible to calculate exactly how much work the gas in the piston could do on the system by calculating some interval over the change in volume. Now, to all these ideas, I am going to add one seemingly obvious physical fact about temperature. If I have something hot and I place it next to something cold, then the cold thing will get hotter, its temperature will increase, and the hot thing will get colder, its temperature will fall. I will never see the opposite process. In other words, no process is possible in which the sole result is the transfer of heat from a colder to a hotter body. If I place a hot thing in contact with a cold thing and do nothing else, I will never see the hot thing get hotter and the cold thing get colder. So with all this in mind, let's introduce the fictitious engine that is going to be at the heart of these next few videos, the Carnot reversible heat engine. The set of thermodynamic states the gas inside a Carnot reversible heat engine visits is shown in the graph on the left-hand side of this slide. I will explain what each of these lines represents in more detail in a moment. However, before we do, remember that the gas inside the engine is a one-component and one-phase system. As such, Gibbs' phase rule tells us that when the gas in the Carnot engine is at equilibrium, its state should be characterized using 1 minus 1 plus 2 independent thermodynamic variables. In other words, 2 thermodynamic variables. So, if we have the pressure and volume of the gas in the cylinder, and if the gas in the engine is at equilibrium, which it is, we have a sufficient amount of information to characterize the gas's thermodynamic state. Now notice that this set of black lines with arrows on them together form a closed loop around the PV plane shown here. This insight, together with our insight based on Gibbs' phase rule, tells us that on completing one full loop around the cycle, we will return to the initial thermodynamic state that we started out from. Having understood this idea, let's consider each of the 4 steps in the operation of the Carnot cycle individually. In the first of these steps, the system, the engine, is put in contact with a heat bath and is allowed to expand. The contact with the heat bath ensures that the gas inside the cylinder stays at the same temperature throughout. In other words, heat flows from the bath into the gas in the tube in order to prevent it from cooling down. We say here that the system expands isothermally, i.e. it expands, but its temperature stays fixed at T2. The next stage in the cycle involves taking away the heat bath and thermally lagging the system. The thermal lagging, shown in red on the diagram of the piston here, prevents heat from being transferred from the universe to the gas in the cylinder or vice versa. Consequently, when the gas expands further, it cools down and the gas's temperature moves to a new and lower temperature. We call this part of the process adiabatic expansion and introduce the word adiabatic to describe processes that occur in our system when heat is not allowed to transfer to the environment. In the next stage of our imagined cycle, we remove the thermal lagging and place the system in contact with a heat sink. This heat sink ensures that the system's temperature now remains fixed at this new lower value T1, which we arrived at the end of the adiabatic expansion phase described previously. During this phase in contact with the heat sink, the gas is contracted and heat thus flows from the system into the sink. We state that in this stage, the gas in the piston is contracted isothermally. In the final stage, we remove the heat sink and introduce the thermal lagging once more, so that once again the system is not allowed to transfer heat to its environment, and so that this final process is adiabatic. During this last step, the gas in the cylinder is further contracted. This drives its temperature up and brings us back to the initial thermodynamic state we started from, as discussed previously. Let's now precisely quantify the heat and work that is transferred between the system and the universe during this cycle of 4 stages. Whenever the gas expands, it does work on the universe. Consequently, during the isothermal expansion and adiabatic expansion phases, the system does work on the universe. We express this total work done during these 2 phases here using the symbol W2, and note that there is a minus sign in front of this because this is work done by the system on the universe. The work is transferred out of the system and into the universe. The volume of the system expands, and the volume of the surroundings thus contracts, in order to balance out the total volume of the whole gas in piston, and rest of the universe 2-phase system. During the isothermal contraction stage and the adiabatic contraction stage, the universe does work on the system to contract the gas. The volume of the rest of the universe thus expands, while the volume of the system contracts so as to keep the volume of the whole fixed. We express the total work done during these 2 phases using the symbol W1, and note that this is now positive because work is now transferred into the gas and because its volume thus decreases. When we take these 2 quantities together, we can get the total work done by the gas in the piston on the universe. We are going to write the negative of this quantity for reasons that will become clear in a moment. So this is going to be equal to W2, the work the gas does on the universe, minus W1, the work the universe does on the gas. Remember, we always want to keep track of whether the system is doing work on its surroundings, in which case we write the work done by the system as it expands, using a negative sign, or whether the surroundings are doing work on the system, in which case we write the work absorbed by the system as it contracts, using a positive sign. Now this quantity minus delta W must be positive. Let's consider what would have happened if it hadn't been positive. we would have had an engine that takes in more work from the universe than it gave out. In other words, the net result would have been an engine that we would have had to drive ourselves by doing work on it. A totally useless engine, in other words. We want engines that do work on the universe. The next stage in this process of quantifying the behavior of our engine is to consider the amount of heat it absorbs from the heat bath and the amount of heat that it dumps out into the heat sink. The first thing to note, though, is that during the two adiabatic stages, the gas in the piston is thermally lagged, and thus heat is not allowed to transfer in or out of it. Now for the amount of heat transferred between the system and the bath and sink. During the isothermal expansion phase, the gas absorbs heat from the bath. Heat is thus transferred from the bath into the gas in our piston. We thus have a positive sign in front of the QH symbol that we are using here to represent the amount of heat that we have absorbed from the bath. During the contraction phase in contact with the sink, by contrast, heat is transferred from the system to the sink. We thus have a negative sign to indicate that QC worth of heat is flowing out from our system during this isothermal contraction stage. If we now add together all the work transferred and heat transferred from and to the system during this loop around the thermodynamic cycle, we get the following. Notice it is minus delta W because the work done by the universe on the system during the contraction phases, W1 is positive, and the work done by the system on the universe during the expansion phases, W2 is negative. Now, at this stage, I am going to assert that if the system moves around a thermodynamic cycle, then the sum of the total work done on the system and the total heat transferred to the system is equal to 0. I will discuss this point in more detail in later videos. It's the first law of thermodynamics. But for the time being, I'm just going to ask you to take it as read that this is true. Now, if we rearrange the final expression shown here and bring the delta W over to the left-hand side and divide both sides by a factor of QH, we get the following. On the left-hand side of this expression, we have a measure of the efficiency of the engine. This is the ratio of the work that the engine does on the universe, W2 minus W1, to the amount of heat that it absorbs. Notice it's plus W2 and minus W1 here, because when we think about the efficiency of an engine, how good it is at lifting weights, driving a car forward, and so on and so forth, we are interested in what happens to the universe and not what happens to the system. On the right-hand side, meanwhile, we have a measure of what this efficiency would be for the Carnot reversible heat engine. We are now going to use the expression that we have just arrived at to demonstrate that there is no engine that is more efficient than the Carnot reversible engine. In other words, in terms of efficiency, Carnot's engine is the dog's bollocks. Let's suppose, however, that this more efficient engine did indeed exist. Our new engine has more bang for its buck than Carnot, so takes in less heat but gives us the same amount of work. In going round the Carnot engine for a given delta W then, QH, the heat absorbed by our fictitious engine, would be less than the QH. The QH prime, the heat absorbed by our fictitious engine, is less than the QH worth of heat absorbed by the Carnot engine. We cannot just decrease QH though, as then QH prime minus QC would be less than delta W, and the total amount of heat and work performed by our engine on going round a loop would not be equal to 0. We thus must also have that in our new engine, the quantity of heat dumped to the sink is less than the amount of heat dumped to the sink by the Carnot engine. In other words, QC prime, the heat transferred from the gas to the heat sink in our new engine, is less than QC, the heat transferred from the gas to the sink in our original Carnot engine. We now run both engines, but run our new imagined engine forward and the Carnot engine in reverse. In fact, we are going to use the work output by our new engine to drive the Carnot engine in reverse. Let's consider the total heat and work transferred between these two engines and the various heat baths and sinks that occurs during this process. Let's start by considering what happens as we drive our new efficient engine around its cycle in the forward direction. We start with the usual isothermal expansion during which the system absorbs QH' worth of energy from a hot reservoir. This is then followed by the adiabatic expansion, during which no heat is exchanged with any reservoir. During these two phases of the cycle, the gas in the cylinder has expanded, so the engine has done work on its surroundings. W2 worth of work has thus been transferred from our fictitious engine and into our Carnot engine. Let's now look at what this work from a more efficient engine does to our Carnot engine. It first drives the gas to contract at the higher temperature. While contracting isothermally, this gas in the piston in the Carnot engine has to pass heat out into the high temperature reservoir. In particular, it has to transfer QH worth of heat out into the high temperature reservoir. Notice this quantity has a minus sign in front of it because heat is being transferred from the gas into the reservoir. This heat is thus leaving the system. Once this is done, the work from the more efficient engine is used to drive an adiabatic contraction of the gas in the Carnot engine. To complete these two phases, the work output by the more efficient engine is all used up by the notionally less efficient Carnot engine, which has W2 worth of work performed upon it. The roles of the two engines now reverse. At the lower temperature, the gas in the Carnot engine expands. The Carnot engine thus does work on the more efficient engine. In order to expand isothermally, however, the Carnot engine must take in heat from the heat sink. Hence, during this isothermal expansion phase, the gas in the Carnot engine absorbs QC worth of heat from the cold reservoir. This symbol has a positive sign in front of it because the heat is transferred from the heat sink into the gas in the cylinder. All that is now left for the Carnot engine to do is to adiabatically expand back to its original volume and pressure and thus complete the cycle. During these two steps, W1 worth of work is transferred from the Carnot engine to the more efficient engine. The work from the Carnot engine is used to drive the isothermal contraction of the gas in the more efficient engine and the subsequent adiabatic contraction. During the isothermal contraction, the gas in the piston dumps QC worth of heat into the heat sink. This quantity has a negative sign because the heat is flowing from the gas in the piston into the sink. Once both loops are completed, the situation in terms of heat and work exchange looks something like this. In total, no work has been done, as any work done by either engine has been used to drive the other engine. QH' minus QH worth of heat has been transferred into the system from the hot reservoirs. This quantity is overall negative because of the inequalities at the top of the slide tell us that QH' is less than QH. One effect of our cycle has thus been to transfer heat out of the gas in the cylinder and into the high temperature reservoirs. The other effect of our cycle involves the transfer of heat between the system and the cold reservoirs. In total, QC minus QC prime plus QC worth of heat has been transferred out of the gas and into the cold reservoirs. Furthermore, the inequalities at the top of the slide tell us that QC prime is less than QC, so this quantity is positive. In other words, heat has been transferred from the cold reservoirs and into the gas. In fact, this heat that has been taken from the cold reservoir has been transferred into the hot reservoir. Hold on though. We said that no process is possible in which the sole result is the transfer of heat from a colder to a hotter body. You can't pass heat from a cooler to a hotter. You thus cannot build an engine that is more efficient than the Carnot engine, as if you could, you would be able to use this new, more efficient engine to drive the Carnot engine in reverse, which would transfer heat from a cold body to a hotter body, which is forbidden. We thus arrive at the conclusion that the Carnot engine is the most efficient engine that there is. The efficiency of this engine is given by the expression shown at the top of the slide. This is the efficiency of any Carnot engine operating between two temperatures T1 and T2. And furthermore, any non-Carnot engine operating between these two temperatures will be less efficient than this. This must be the efficiency of any Carnot engine, as if we were able to create a Carnot engine with an efficiency different to this one, we would be able to pass heat from hotter things to colder things by using the more efficient engine operating in the forward direction to run the less efficient engine in reverse. This passing of heat from hot things to cold things is prohibited. The critical consequence of all this is that we can use the Carnot engine to create a universal calibration for temperature, which will be the subject of my next video. Thank you for your attention.